Alright, hey guys, I'm going to do a quick run through of short task 3, just to give people a little bit of a hand, a bit of a pointer with this task, which is looking at determining the amount of cooling power required for different tasks. The example given is in a winery, but as I've written at the bottom of that task, you can also do it in a dairy example, and I'll give a couple of pointers for that as well. Here is a blank spreadsheet which we'll be populating, hopefully with a few formula, which I'll be doing on the fly, so hopefully I don't get caught up myself. Seemed to get through the last time when I was worried about that. So let's go to the subject page and look at short task 3. It's actually relatively simple. There's a fair bit of words here, but what it is based on the production facility we made in short task 1, and it asks us to calculate the chilling power required. If you cut to the chase, if there's 1, 2, or 3 simultaneous fermentations, these fermentations take place in the fermenters that we made in short task 1, where they're filled to 60% capacity. So we need to know what the volume of those tanks are and what 60% capacity would be. So we get a volume. Gives us a fermentation rate of 1 Beaumet per day. So how much cooling is required to maintain the temperature of the ferments? So we don't want the ferments from warming up. So what cooling power allows us to keep them at a set temperature. And at the same time, we are chilling juice. We want to drop it by 15 degrees over a 24-hour period, and it says the tanks are uninsulated but not exposed to the outside. Okay, so let's have a look here in the notes, and we go to refrigeration calculations, and what this gives us is 2 methods for calculating this. It gives us the AGR3VE method, and also gives us the method from White et al. Now the AGR3VE method could actually be used for any substance really, because it's based on core physics. So if we're doing a milk example, we could use that one. I actually recommend that you use the white one. So if you're doing wine, you can utilize these ones here, and they're the ones I'll be going through in the spreadsheet. But equally, you can very simply use the AGR3VE method as well. So let's have a look here. Calculate cooling required for fermentation. You have a 10,000 litre ferment running at 1 Beaumet per day. For the calculation, you actually need it on Beaumet per second. So we convert Beaumet per day to Beaumet per second. So 1 Beaumet per day is 0.0000125 Beaumet per second. That's how much the sugar will drop. What cooling is required to prevent the ferment from warming? So here we use the formula Q equals the mass, in this case we put in the volume, times the specific heat capacity of the substance. The actual heat or the energy given off from this ferment, which is 10 kilojoules per litre per Beaumet. So for every litre being fermenting 1 Beaumet, it gives off 10 kilojoules of energy, and we multiply it by the fermentation rate, which is 0.000125 Beaumet per second. So we've got the amount of energy given off by litres, we've got the volume in litres, so we can see the kilojoules per Beaumet, and then we know how many Beaumet per second, so we'll be getting the kilowatts. So the joules per second, joule per second is a watt. So that's fairly simple. So we just need the volume, the energy given off, and the Beaumet. What if we were just looking at chilling something? Well, let's use if we're doing the milk example, we'll get back to wine. If we're doing the milk example, we want to work out what kilowatts of power is required to chill 10,000 kilograms in an hour, or 10,000 litres in an hour, from 100 degrees after pasteurization to 4 degrees. So we want to drop it 96 degrees. So we can use this formula here, Q equals M times specific heat capacity here with CP, times temperature 1 versus temperature 2, which gives us a delta T, a change in temperature. So we want to work out what the cooling power is. So the mass flow rate is the kilograms per second that we want to chill. So in this case, you want to work out how many kilograms 10,000 litres of milk is. So you just need the density of milk, and you'll be able to find that very simply. So if you have 10,000 litres, multiply it by the density of milk, and you'll get the kilograms of milk. We want to do it in 1 hour. 1 hour is 60 minutes. 60 minutes, each minute has 60 seconds, so it's 3,600 seconds. So we divide 10,000, or whatever the weight of the milk is, divided by 3,600 seconds. Gives us the kilograms of milk we need to cool per second. And then we need to know the specific heat capacity of milk. Now I've given the specific heat capacity for grape juice as part of these notes, but on Google we can quite simply go to like the engineering toolbox, which is just an absolutely awesome website, and here it's got the specific heat capacity of like everything you can think of. And I'll scroll down here. Look, there's even mercury. I mean, I hate to think what you'd be doing if you needed that. Here's milk. Specific heat capacity of milk, 3.93. So we go back to this. We plug in 3.93. It takes 3.93 kilojoules of energy per kilogram of milk to lift it 1 degree, or change the temperature 1 degree. So that's what we need to take out to chill it. So we'd simply get the mass of our milk multiplied by 3.93 times our change in temperature, which is 96 degrees, and that would give us the kilowatts. So there we are for a milk example. That's very simple. All right, let's go back to wine. I'm going to go now down to the White et al. Calculations. This is from engineering for winemakers. Let me do this. Flick. All right. Mass cooling load in kilowatts is the product of the grape tonnage per 24 hours and the required temperature divided by 24. So chilled by 10 degrees. All right. So here's the example. So we want to chill 5 tons of grape must by 10 degrees. The required kilowatts would be 10 for 10 degrees times 5. So we want to chill 5 tons by 10 degrees. And we divide by the number of hours for which we're doing it. And that's 24. That gives us 2.1 kilowatts. If we were doing it in 1 hour, obviously we wouldn't divide by 24, we'd divide by 1, and that would give us 50.4 kilowatts. And what it says here is this is very similar to the AGR3VE calculation. And here it is here. So here we use the AGR3VE, which is a slightly more complicated calculation, but not really. It's just the mass flow, which is the weight of our must over per second that we need to chill, times the specific heat capacity of grape must, which is 3.7, which is very close to milk, times the temperature difference, 10 degrees, 51.8 kilowatts, that one gives us. So almost identical to the White method. So you can use either, but I'm going to use the White method in this one here. All right, so this is our must chilling. So we might as well do our calculation for our must chilling. Let's go back to, here it says here. 1 juice chilling full tank will be undertaken when a maximum of 2 tanks. All right, so the temperature of the juice needs to be dropped by 15 degrees over the course of 24 hours. All right, so let's go to our chilling. Let's just do, when I'm doing my spreadsheets, I like to do things, lots of labels. Chilling tank. So for all the different scenarios, we're only ever chilling 1 tank. So what's the volume of that tank? Well, from memory, it was a 2 meter diameter, 2 meters high. So the volume of a cylinder is the height. Might as well, let's just do it all. Height of tank. put that in meters. What's the diameter of the tank? Diameter of tank in meters. It's 2 and 2. And so volume of tank in meters cubed. So what's that? Equals the height, which is this one, times, what is it? The area of the circle times the height. So pi r squared, so we need the radius squared, so its radius is half the diameter, squared times pi, 3.142, or in Excel you can just do pi, bracket, bracket, that gives you pi. So that's the volume of our tank in meters cubed, 6.28. Let's get rid of some decimal points, annoy me. So 6.28 cubic meters, or 6,280 litres thereabouts in the chilling tank. So that's how much juice we want to chill. I'll put delta T. So this is the change in temperature. And it said we wanted to drop it by 10 degrees. Time of chilling in hours. Let's put that in degrees. Time of chilling, we want to chill it over 24 hours, I think the example said. Alright, so we want to chill 6.23 cubic meters of must by 10 degrees over 24 hours. So we go back to the notes and just remind ourselves of that formula. Yeah. The chilling times the tons of must times the time. Alright. So we need to convert our literage to tonnage. So we can make a sort of a guess here. So we know what the fruit, so the fruit came in and we converted it to juice. So let's say there was a 60%, let's say, just sort of thinking, if we had, say, a ton of fruit and we convert it to juice, what volume is that? So what volume would we need? What weight of grapes would we need to get 6.28 cubic meters of juice? Let's say it's let's say it was 10 tons. Weight in tons, 10. So in your report, you just need to write an explanation of where you got the figures. So we'd obviously know the weight of it if it came into the winery, but here we've only got a volume. So let's say we use 10 tons. That sounds about right, and we get a 62.8% yield of juice. So then we just kilowatts. Let's put chilling capacity equals the weight times the time. No, weight times the temperature difference divided by the number of hours. 4.16 kilowatts. Make sure all those numbers are correct. Hang on, let's have to go here. No, we need to drop it 15 degrees over 24 hours. And okay. So I just because I've referenced all the cells rather than just typing the numbers into the formula. I can just quickly just change that there, and it changes it. So 6.25 kilowatts is required to chill that juice over a 24-hour period. All right. So we need a minimum in this winery, a 6.25 kilowatt chiller to do that chilling operation. So if we wanted to increase the amount of time it took to chill that down, like if we were having to take 2 days, our chilling capacity is halved. Let's say we were happy with 60 hours, only 2.5 kilowatts. So using this, you can quickly sort of change change the figures and see how that would change the chilling capacity in your facility. All right, let's have a look at a ferment. Let's get this same tank. Ferment is a little bit easier because we're actually talking in volume. And in this case, our it's 60% full, I think. So, oops, fill level is 60. So I'll do that 0.6 and I'll turn that into a percentage. So volume of ferment in meters cubed. So what I've said is the fuel level in that tank, because that's what the question says, is that the ferment level is 60% of the volume of the tank. So we know the volume of the tank. We calculated that. So I do that times the percentage. So we've got 3.77 cubic meters of ferment, or 3,770 litres. All right. We'll go back to our notes. What else do we need? All right, according to this method, the kilowatts of cooling required is the volume in kilolitres. We've got that already. It's the same as meters cubed. Multiplied by the Beaumet drop per day divided by 10. That's easy. Then it says, aside from gains mentioned in juice chilling, let's have a look. We'll have a look at that in a minute. Other heat gain can be from people and lights. All right, so if there's a person in the winery, you've got to add 0.25 kilowatts of cooling power required. And if there's lights, it's 0.015 kilowatts per square metre of tank area. We'll get to that one later. Let's just work it out for the ferment. So it's the kilolitres of volume. We've got that, same as the cubic metres, multiplied by the Beaumet drop per day divided by 10. All right, so ferments, what does it say? Ferments are to run at 1 Beaumet per day. Okay. All right, so it's just our kilolitres multiplied by 1 divided by 10. It's easy. Okay. Beaumet drop. See how methodical in this? Beaumet drop per day is 1. So what I call it before, chilling capacity equals kilolitres, which is the same as our cubic metres. There. Multiplied by a Beaumet drop per day divided by 10. Whew, tiny. 0.38 kilowatts. So that's easy, isn't it? So that's a lot easier. A lot less power just to keep a ferment. I suppose it's a much smaller amount. Up here in our weight of tonnes, we actually just get the density of grape must and multiply that by the volume. So that would be the grams per mil or the kilograms per litre. So rather than guess, you could actually get the density of grape must and multiply the volume by that density. That would be a much better way of doing it, Alistair. But as I said before, if you received it in the winery, you would know the tonnage anyway. Maybe you just subtract, if you've crushed destemmed it, subtract the losses from the rackers. So just sort of guesstimate the weight of the rackers, or you could even weigh them. All right, so in this winery with one tank going, we need 0.38 kilowatts of ferment for the ferment and 6.25 kilowatts for chilling of the tank. So let's put total chilling equals that plus equals that plus that. All right, then it says, despite there being no heat gain from the pump, because we're not pumping it around, I'm just reading as I go. There's probably been no heat gain from the pump. A heat gain from the surrounding environment is greater than with a heat exchanger. If the tank is insulated with a minimum of 40 mils of insulation, then the heat gain is the square metre surface area of the tank divided by 150. However, if the tank is inadequately insulated, like in this question, but inside an enclosed winery, then the heat gain is the square metre surface area of the tank divided by 10. If it's uninsulated and exposed to the outside, then it's the surface area divided by 6. Whew. So let's get the surface area of our tank. Surface area of the tank. All right, so surface area of the tank. So we need the circumference of the base of this cylinder, which is 2 pi r. So the radius times 2 times pi. So it's the diameter times pi. And then to get the overall surface area, we multiply by the height of the tank. So that's how you get the surface area of the tank. It's the circumference of the circle at the base of the cylinder, or the top of the cylinder, times the height. And that'll be in square meters. Oh. So it's 12.56 square meters. So let's say heat gain from environment equals, we're uninsulated but inside an enclosed winery, so it's that divided by 10. Woo! 1.25 kilowatts. So we need to add that onto there. People, kilowatts. People, number. So how many people are in this winery at any one time? Chilling for people. So each person in the winery adds 0.25 kilowatts. So it would be that times 0.25. So let's say there's 2 people running around. Adds 0.5 kilowatts of chilling required. That plus that. And then it uses the same process to work out how much the lights would add. So it's lights based on the surface area of the tank. So the first one part of the question is how much chilling is required for one chilling tank and one ferment. Well, assuming that it's uninsulated but not exposed to the outside environment, there's 2 people in the winery most of the time, we need 8.38 kilowatts. So you can use the same methodology if there's 2 ferments and 1 chilling and 3 ferments and 1 chilling. So that's pretty easy to work out. You need to double check if I haven't done anything wrong. And also you could change it for the number of people, but in your report you just have to say how many people you factored in. And also the lights, you've got to do the lights yourself as well. So please double check if I have made any mistakes. But as it stands, if we wanted to run 1 chilling tank and 1 ferment at the same time, we'd need a chiller with at least 8.4 kilowatts of chilling capacity. So it's pretty awesome that you can do those calculations. And again, if you're a milk person, you can just do the same thing, but with milk. So you wouldn't have a ferment unless you might be doing yogurt fermentations or something. But here it's chilling milk, and I talked about how you can do the calculations for the chilling of milk as well.